Hello, my name is Ellis Brown, and I'll be speaking today about linearly constrained separable optimization using two packages that my team has developed. This work was done in conjunction with Nicholas Maley and Michael Kokendorfer at BlackRock AI Labs. We'll begin by going over our two packages, PiecewiseQuadratics.jl, which allows for the representation and manipulation of univariate piecewise quadratic functions with a special focus on optimization. And LCSO.jl, which solves a linearly constrained separable optimization problem using ADMM. We've open sourced both of these packages, and you can find them on GitHub. And actually, after conversations with various members of the Julia optimization community, we've decided to create a new GitHub organization called Julia First Order to host these packages and other related first order methods in Julia. So we'll touch on that briefly. We originally created these packages and the corresponding methodology to solve a certain class of portfolio construction problem. We detail this in a paper we released in March of this year, which you can see linked on the bottom right. So we'll conclude with a peek into portfolio construction and some of the methodologies outlined in this paper to help motivate these packages and provide a concrete application of them. So again, PiecewiseQuadratics.jl is a package for the manipulation and representation manipulation of univariate piecewise quadratic functions, where each piece takes the standard quadratic form of px squared plus qx plus r, defined on some interval represented by a lower bound and upper bound. Note here that we are defining the function to be infinity outside of these bounds. We implement several methods that are useful for optimization, such as the sum, the derivative, the convex envelope, and the proximal operator, and many more, which you can see in our API documentation. So I want you to consider, when we're talking about this package, applications to cost functions, where we might be able to represent in a cost function in much higher fidelity than, say, a piecewise linear function, while still remaining computationally tractable. So here's an example piecewise quadratic consisting of 5 quadratic functions, each bounded on an interval. And note that they are listed in increasing order of their interval. So to represent this using PiecewiseQuadratics.jl, we represent each quadratic piece as a bounded quadratic. This is just a standard quadratic function defined on some bounds by an interval. And the piecewise quadratic f is just a list of these bounded quadratics in order. So we can see here that the first line, the first bounded quadratic, is defined on the lower bound of negative infinity to an upper bound of 3. The quadratic term is 1. The linear term is negative 3, and the constant term is 3. And we can see that this translates for each of the quadratics defined above to the line below. Now, of course, we can evaluate this piecewise quadratic f by just calling it with a real value. And if we were to save a bounded quadratic as a variable, we could do the same by calling it with a real value. And we defined a number of utility methods. One that I want to call out is getPlot, which allows for interfacing with your favorite plotting library. So here we're using getPlots. And I'll note that getPlot has a number of keyword arguments that you can see in our API documentation. And it returns an XY time series that just gets passed into the plot function. So here we're using getPlot to plot the piecewise quadratic that we defined on the previous page in the first line, and that is plotted in black. And on the second line, we're plotting a simplified version of the convex envelope of this piecewise quadratic f. So we can see here that this saves a lot of time. This would be quite complicated to define manually. And this is just very, very simple. Yeah. So next, we'll talk about LCSO.jl, the package that motivated PiecewiseQuadratics.jl. So we're focusing on linearly constrained separable optimization problems, or LCSO problems. Now, LCSO problems take the standard form as follows. The decision variable x is an n-vector. We have m linear constraints, and the objective f is separable about the dimensions of our decision variable. So we see that there are n terms in the summation. Now, LCSO problems can be solved using ADMM, and they can be solved exactly when our separable functions fi are convex, and it can be solved only approximately when they're non-convex. And I will point you to the paper for full details on this. LCSO problems can also be represented in an extended form, which is basically the same as the standard form, except it's quadratic about x. We can see here that the p is symmetric, positive, semi-definite, n by n, and the q is an n-vector. So this extended form of an LCSO problem can be reduced to the standard form using an eigen decomposition. And again, I will point you to the paper for full details on this. So the LCSO.jl package solves these LCSO problems using ADMM. It can work with both the standard form or the extended form. We can solve both convex and non-convex problems, although again, convergence is only guaranteed for convex problems. And in practice, we see that it converges to moderate accuracy quickly, even when the separable fi are quite complicated. And this is nice because we're working under a very limited set of assumptions. One limitation, though, is that we currently require the separable fi to be piecewise quadratic, as defined using our PiecewiseQuadratics.jl library. Now, in theory, this limitation could be removed, and we could support any functional form that has a proximal operator defined. So here we'll go over one example of the usage of the LCSO package. So we'll define an arbitrary problem with 4 features and 2 constraints. So we're constructing some random problem data, and we're ensuring that P is positive semi-definite. And here is the extended form which we're constructing this problem in for reference. So to note, we have our P, we have our Q, we have our A and our B. The only thing we're missing are the Fi. And again, because the F needs to be separable across the dimensions of our decision variable X, and there are 4 dimensions, there are going to be 4 Fi. So we'll define the Fi using our piecewise quadratics library. Now, we're going to require that x1 has to be in the union of the interval between -1 and 2, and 2.5 to 3.5. And if it falls in the former interval, we'll give it a quadratic penalty, and in the latter, we'll give it a linear penalty. And again, in any region of over x that is not listed in one of these intervals, we're taking an infinite penalty. x2, we're going to require that it falls in the interval of -20 to 10. So we're creating a piecewise quadratic with a single bounding quadratic that has just a constant 1 in that interval. And again, infinite penalty outside. Similarly, we'll require that x3 has to lie on the interval of -5 to 10. So this indicator function here is just a utility function that we've defined that basically translates exactly to the form of f2. So it just saves some code there. So it translates to a piecewise quadratic with a single bounding quadratic on the interval of -5 to 10 with a constant penalty of 1. And we'll require that x4 has to be exactly 1.231. And we do that by making an indicator where the lower and upper bounds are the same. So the last thing we need to construct our problem is to combine these each of these f's into a single f, and we create a ADMM parameters object. And again, look at the API documentation for full details here. But we just pass in all of the pieces of this extended LCSO form that we need: the P, the Q, the A, the B, and our F's. And we can just solve it by using the optimize function on this params object. And it outputs the optimal variables as well as the stats from the ADMM run. So we can see here, this is just from one example run, that the optimal x falls in the bounds we defined. The x1 is in the first of the two intervals. x2 and x3 fall right in the bounds we defined, and x4 is exactly 1.231 as we defined. So we see many applications of this package and this methodology, one being portfolio optimization, obviously, as we'll see later. Another one might be radiation treatment planning, where we're optimizing the radiation intensity pattern for cancer treatment that best achieves clinical goals like the dose distribution. Another might be dynamic energy management, where we're optimizing the power produced and consumed by a network of devices over time. And many more. Now note, if you have a PDF version of this, these are hyperlinked to examples. So again, we've created a new GitHub organization called Julia First Order to host these packages and subrelated packages. Some that we plan to migrate are ProximalOperators.jl, ProximalAlgorithms.jl, and StructuredOptimization.jl from our colleagues at KU Leuven. And we think these especially will go hand in hand because, as I mentioned, one current limitation of the LCSO.jl package is that we require the separable f's to be represented using our PiecewiseQuadratics library. But in theory, it could be extended to any functional form that has a proximal operator defined. So, yes. And I do want to call out, thank you, Miles Lubin, for suggesting we create this organization in the first place, and thank you for putting us in touch with the right people. I think we're all very excited to get this off the ground. So we'll conclude with a brief dive into portfolio optimization. The original formulation of portfolio construction as an optimization problem dates back to the 50s, and it's often referred to as mean variance portfolio optimization, or commonly risk minimization. So it takes the following form, where the decision variable represents the fraction of the portfolio value that is in each of n assets. And so we require the constraint here, we require that they sum to 1. Note that negative values are allowed, and that would indicate that we're taking a short position on that asset. The vector mu represents the expected return for each of our n assets. Now this makes the term on the right-hand side of our objective, this makes that the expected portfolio return, or the mean return. Sigma is the covariance matrix of our asset returns. And this makes the left-hand term of our objective the variance of our portfolio's return. So we have the mean return and the variance of the return. Finally, gamma is a risk aversion parameter, which allows us to toggle how much we want to penalize a risky or a high variance solution. So again, this is we're minimizing the variance minus the mean portfolio return. And this is the most basic formulation. One thing we might want to do is to add in additional costs or penalties here to make it more realistic, like taxes or trading costs. So we see here that sometimes these might be, they might often be separable across our decision variable x, which again is the percent of the portfolio in each of our different assets. So if we can define any cost function that is defined per asset, then this fits perfectly in as an extended form LCSO problem and can be solved using our library. So some example costs that we might introduce that are separable would be trading costs, where this is a realistic one where it's not free to trade. We might be charged a certain cost for more in demand assets, or a lower cost for less in demand assets. So here we would be charged no penalty if we don't trade, and we'd be charged some penalty if we do. We might be charged a holding cost. So this might be, say, in the scenario that you're shorting a stock. To short a stock, you need to borrow the assets up front, and you're charged a fee to hold them. So we'd be charged no fee if we're not holding any, and we'd be charged some constant fee for a specific asset if we are holding it. We might want to put on position limits to set a maximum or a band on the percent of our portfolio we want in a certain asset. So take this form, and we might want to add in some combination of these different ones, or things that are much more complicated than this. I note that these might be non-convex, as you can very well tell. And again, our LCSO package should be able to solve these approximately. The one smart way to handle this is to relax the problem by replacing each Fi with its convex envelope, and then using the result of this to recover a solution to the original problem. Again, this is very easy to do if we've used our PiecewiseQuadratics library to represent the F, because we've defined the envelope operator. So with that, I will open it up for questions. Thanks.